Exactly. Today we're jumping into a really neat physics problem. Imagine trying to shoot something super tiny, incredibly fast, through this invisible tunnel of forces.
And you need to know exactly how fast to shoot it so it makes it through.
Right. We're talking about a negatively charged particle, and it's navigating this constant electric field between two charged plates.
The classic scenario.
Our mission to really unpack this, figure out the path it takes, and calculate that absolute minimum speed it needs to succeed.
It's about understanding the interplay, the field, the force, the motion.
And hopefully you'll walk away not just with the answer, but really getting how these forces shape things on a microscopic level. Okay, picture this. Two flat parallel plates, like walls, but tiny. They're just 1 centimeter apart.
Okay.
One's got a positive charge, the other's negative. And into this very narrow gap, we're launching our particle.
A specific particle.
Yeah, not just any speck. This one has a negative charge, -2 coulombs, which is pretty significant, and a mass of 0.5 kilogram.
And that negative charge is crucial, as we'll see.
Definitely. Now, these plates, they aren't infinitely long. They stretch for 8 centimeters.
Okay, so it has a defined path length.
Right. And between them, because they have this uniform charge spread, 2.65 times 10 to the -8 coulombs per square meter, they create a constant electric field.
And that constant part is really key.
Yeah.
Between parallel plates like this, the field is uniform. Same strength, same direction, everywhere inside that gap.
Like gravity near Earth, sort of. Predictable.
Exactly like that. It makes the calculations much more straightforward than if the field was changing all over the place.
Okay, so the big challenge, the thing we need to figure out, is the minimum speed horizontally that this particle needs to travel the whole 8 centimeters without smacking into the bottom plate.
And it starts right in the middle of that 1 centimeter gap.
Precisely, dead center. So it only has 0.5 centimeter downwards before it hits. That's not much room for error.
No, it really isn't. Tight constraints.
So we've got the setup, particle, negative charge, constant field. What's actually pushing it around in there? What forces are acting on it?
Right. Let's break down the forces. First, the electric field itself. Conventionally, electric field lines point away from positive charges and towards negative charges.
Okay.
So if we assume the positive plate is on the bottom and the negative one is on the top, which seems implied by the goal of not hitting the bottom plate.
Right. Otherwise, it would be pushed away from the bottom.
Then the electric field lines point upwards from bottom to top.
Upwards. Got it.
Now, here's the twist. Our particle is negatively charged.
Ah.
And the rule is the electric force on a negative charge is opposite to the direction of the electric field.
So field lines point up.
Force points.
Downwards. Unequivocally downwards for our particle.
Okay, so that explains why it's in danger of hitting the bottom plate. It's being actively pushed down.
Correct, even though the field lines point up. So let's think about the motion. It's launched horizontally, right? So no initial push up or down.
Its initial vertical velocity is 0.
And horizontally, are there any forces?
Nope. Neglecting air resistance or anything like that, there's no horizontal force mentioned. So constant horizontal velocity.
Okay, constant speed sideways. But this constant electric force is pulling it downwards.
Which means constant acceleration downwards.
Constant horizontal velocity, constant vertical acceleration. That sounds familiar. That's a parabola.
Exactly. Just like throwing a ball horizontally off a table, gravity pulls it down in that familiar arc. Here, the electric force does the same job.
You can almost picture it curving downwards towards that bottom plate. It makes total sense.
And this actually leads to something interesting about how the problem was likely set up. Often, physicists will define the positive y-axis direction to match the acceleration.
Oh, so they'd make down the positive direction here.
Why possibly? The common trick. If the acceleration is downwards, you define down as positive y. Why?
Makes the math easier.
Bingo! Your acceleration A is then a positive number in the kinematic equations. You avoid scattering minus signs through your work. It just streamlines the algebra.
Clever. Align the math with the physics.
It's good practice.
All right, we understand the path, the forces, now for the numbers. How do we actually calculate that minimum speed? Where do we start?
First things first, we need to know the strength of that electric field.
Hey,
we have the formula for parallel plates. E equals sigma over epsilon naught.
Sigma is the charge density they gave us.
Right, 2.65 times 10 to the -8 coulombs per square meter. And epsilon naught is the permittivity of free space, a constant.
Which is about 8.85 times 10 to the -12 farads per meter right
That's
here.
the one. So you plug those numbers in. E, 2.65 by 10 to 8, 8.85 by 10 to 12.
Okay, crunching those numbers.
It comes out nice and clean, 3,000 newtons per Coulomb.
3,000. So that's the strength of the field pulling, or, well, setting the stage for the pull.
It quantifies that invisible force field, yes. And is a reasonably strong field, definitely enough to have a significant effect on a charged particle.
Okay. Now, how hard is that actually pushing our specific particle downwards? We need the acceleration, right?
Exactly. Step 2, find the acceleration. We know the electric force is Q times E, and from Newton's second law, force is also mass times acceleration. We can rearrange that to solve for acceleration. Let's look at our values. Q is the charge. So magnitude of Q is 2 coulombs, E is 3,000, mass m is 0.5 kilograms. That's 6,000 divided by 0.5, which is 12,000.
12,000 meters per second squared, downwards.
Wow, 12,000 meters per second. That's huge. That's like, what, over 1,200 times the acceleration of gravity? It's immense. It really highlights how strong electric forces can be, especially compared to gravity at this scale. Particles can be whipped around incredibly quickly.
No kidding. Okay, so it's accelerating downwards at this insane rate.
Yeah.
How long does it actually have before it hits the bottom plate? It only has that half-centimeter drop.
That's the crucial time constraint.
Yeah.
Step 3, find the time tie.
The real trick to solving a problem like this is to split it into two completely separate parts. Horizontally, there's no force, so its speed is just constant. But vertically, we have that constant electric force, which means we have constant acceleration. This right here is the key that unlocks the whole thing. Because the particle starts moving perfectly horizontally, perfectly flat. It has zero initial velocity going up or down. And that just makes the math for its vertical drop so much simpler. So the particle starts right in the middle of that 1 centimeter gap, which means it only has to fall half a centimeter, or 0.005 meters, before it hits the bottom. We can use a standard kinematics equation for motion with constant acceleration to figure out exactly how long that fall is going to take. And the answer is an incredibly short amount of time. The particle has just over 9/10,000ths of a second before it hits that bottom plate. In that tiny fraction of a moment, less time than it takes you to blink, it has to travel the full 8 centimeter horizontal length of the plates. Any slower, and it's game over.
That's it. The combination of the strong acceleration and the very small distance dictates this incredibly short flight time.
Wow. Okay, so in that tiny window, that fraction of a millisecond, it has to travel the full 8 centimeters horizontally.
Correct. Which brings us to the final step, calculating the minimum required horizontal velocity, Vx.
And since the horizontal velocity is constant, it's just distance equals speed times time.
Simple as that. T is 9.13 by 10 to 4 seconds. So rearrange for Vx, 87.6 meters per second. That's fast.
What is that in miles per hour? Like,
Yeah.
multiply by 2.2, nearly 195, 200 miles per hour.
Roughly, yes. Around 196 meters.
For this tiny particle, through a 1 centimeter gap in less than a millisecond, that's seriously zipping along.
It has to beat that downward acceleration over the 8 centimeter length any slower, and it hits the bottom plate before it clears the end.
Incredible. It really paints a picture of the dynamics inside things like particle accelerators or even old CRT televisions, maybe.
Absolutely. Steering beams of charged particles accurately requires precisely this kind of calculation, balancing field strengths, particle properties, and velocities.
Now, just to explore this a bit, you mentioned the negative charge was key. What if, hypothetically, the particle had been positively charged instead? Same mass, same magnitude of charge, just positive.
Interesting question. Let's think back. The electric field lines still point upwards from the positive bottom plate to the negative top plate.
Right.
But now the force on a positive charge is in the same direction as the electric field line.
So the force would be upwards.
Exactly. Instead of being pulled downwards towards the bottom plate, a positive particle launched horizontally would feel an upward force.
So it would curve upwards towards the top plate.
Precisely. It would still trace a parabolic path, but the parabola would open upwards. The whole problem flips.
The danger wouldn't be hitting the bottom plate, but the top one.
Correct. You'd do similar calculations, but the vertical displacement you would be measured upwards, and you'd be finding the minimum speed to avoid hitting the top plate.
And looking forward, as we get better and better at creating and controlling these electric fields with more precision, what completely new applications might we unlock? What possibilities open up when we can steer the very small, very fast, with near-perfect accuracy?
That's the exciting frontier, isn't it? Pushing the boundaries of control at the nanoscale.
Something to think about.